Thank you. Thank you. Thank you. Or stay. All right, we're just getting started.
Mic test? Yeah, okay.
I'm here.
No, I'm looking for
Sorry about that. Share. All right. Thank you so much. All right, everyone. Welcome to Robotics X Tokyo's, what month is it? April event. As you may know, we do events every month. This month, we're doing Robotics X Space, and that is outer space, not any other space. So let me just chat a little bit about first of all what the organization is and who our speakers are tonight. So I started this organization with a couple of other folks. Marco Simic is one person who's not in Japan anymore, and Tim Trahan and Nico and a few other members started about a year and a half to 2 years ago. And it originally sprang from something that I used to do back in Silicon Valley called Silicon Valley Robotics. So there's a event out there that they run called Bots and Beer every month, where we used to just go and buy like 20 pizzas from Costco and get a bunch of beers and, choose a company, one of the robotics companies in the Silicon Valley area to hang out at, do demos, things like that. That was from about 2012, 2013. And then when I moved to Tokyo about 3 years ago, we spun this one up. So it's been great. And we basically exist to bring robotics companies together for networking, sharing of ideas, and hiring, things like that. And it's been a big hit over the past year or two. So thank you for attending. Every month we do themed panels, or we have a casual meetup at a bar somewhere. This time, as I said, we're doing Robotics X Space. And tonight we're going to talk about mainly two different companies in the robotics space industry in Tokyo. One of them is more of an international company. So first, why don't you go ahead and introduce yourself? Maybe we can go right into it. It'll save time.
check, mic check. Just today, I want to quickly. So I'm Louis. I'm from France. I work at JAOPS, a company who does mission control services for space exploration missions, Earth orbit, astronaut support, and lunar exploration. Today, as an introduction, I'll quickly go through several of the lunar exploration rovers I've been involved with. So just throw at you a bunch of pictures, go rather quickly, and then we can come back to it with questions on the topics that you're interested. And in the second half, I'll talk more about JOPS itself, the kind of services we provide, and hopefully that creates discussion as well. So first up is this quick video to show you the first aspect I was involved in was in Hakuto. So more than 10 years ago, one of the first employees I joined when we were maybe less than 10 employees, and then grew the company to more than 100 at the time that I left, and now it's a lot more. So the first of the rovers that you see here, going quickly on the screens, kind of gives you a sense of all the different iterations and the hardships of integrating those rovers, building them, testing them, designing them, building them again, testing them again. There's a lot of images of different types of tests, whether they're vibration tests, thermal vacuum tests, anechoic chamber tests you saw just now. And you can see the rover design itself changes and evolves over time. Where we always have this 4-wheel rover platform. And then we refined it to be able to survive through the rigors of space. We refine it to make it smaller and smaller. Every kilogram we sent to the moon, the target was about $1 million per kilogram. So very often my job was, okay, spend 2 weeks to reduce 2 or 3 grams for the rover. That's a good use of my time. So we did everything from the design, and this is the final version that you see here now. We shipped it to India. The lander at the time of iSpace didn't have its own lander. So we contracted a lander company in India, and we sent the rover there. Intense weeks that we spent teaching them how to take care of the rover, put it on their lander. And then we went back to Tokyo, and with the twin of the rover, we did those kind of field tests that you saw. Can I go to the next one? All right. So that was kind of an overview, and I don't have this on my screen. Can I remove this? Okay, nice. That's not me. So a quick things just to focus on the different types of tests we've done, and focus on the types of, show you some pictures of the different rover iterations. This field test was in the sand dunes, south of Tokyo, Nakajima sand dunes. It's a beautiful place. It looks like the moon. There's no vegetations, only sand. And we use this as a test bed for driving the rover 500 meters. And in this particular test, we're checking mobility, trafficability, making sure the browser wheels operate correctly on different types of slopes, and that our algorithms are recording the slip of the rover. So we have a ground truth to know exactly the position of the rover. And we compare that to what the rover is thinking, the number of re-rotations and things like this. We also do a lot of hazard detection and avoidance, because if we crash on a rock, or if we drop into a crater on the moon, there's nobody to pick us up. So I was involved in this hazard detection and avoidance camera. It's like a time-of-flight camera, so a 3D sensor at the front of the rover, who can automatically detect the depth. You see it color-coded here. And the issue with this type of sensor is their illumination conditions on the moon are really tough. So we did a lot of testing at night with a powerful light source. And you can see on this graph, left side, you have a nice, no noise, but as soon as you have a strong sunlight, 100,000 lux, for example, you see noise, you see ghost pixels. And so we have to teach our algorithms to remove that noise and to not make emergency stop all the time.
Can I jump in with a quick question?
Yeah.
So what would you say the method would be for detecting a ditch versus a pile of something? Because that seems incredibly difficult if you're, say, about 5-6 meters away and all you have is a LiDAR or time of flight sensor. Yeah. You don't have a good view into that hole.
Exactly.
So I don't know if you have any ideas of.
We wrote a paper about it, so I can put that in the link somewhere, or if people are interested. But in a nutshell, this is just an emergency stop sensor. So the range is just 1 or 2 meters in front of the rover. And once you get to that range, you can see that there's a depression, that there's no more ground. If there's no more ground, it's probably a ditch, so you stop. And if there is too much ground, it's probably an obstacle, and you stop also. So yeah,
awesome.
This is happening in real time on board the rover. The other key aspect was the camera system I worked on. So one of the key features of this rover was having a omnidirectional awareness of the surroundings, again, for avoiding hazards, but also for knowing where you want to go, and for the scientists to pick out targets that are interested to visit, make the most of the limited time of the mission. So we had those 4 cameras, and we went and did a field test in Pittsburgh at Robotics, was our partner at the time. And they have this rock quarry that really looks like the moon also, with this kind of field test at night. And you can see in this quick image kind of what the rover sees from the point of view. And what I want to show you there is the quality is very bad, because the bandwidth on the moon is so limited that we have to heavily compress. So we had onboard real-time H.264 compression in hardware for the 4 cameras to reduce that color stream to just 2 or 3 frames per second, and a total of 50 kilobits per second. So very tiny, but it's enough for human operators, human eyes, to figure out where the rover needs to go and what obstacles to avoid. So I'm skipping like several years down the road, but we did a lot more testing. And unfortunately, this rover, that was part of the Google Lunar X Prize competition. There was no money on the side of the Indian lander. So we brought back the rover to Japan, canceled, and it ended up in the Smithsonian Museum. So hopefully we can go and see it again. And that's part of the reason why iSpace started to make its own lander now. And as you know, they've been quite successful doing that. So on my side, I left iSpace around that time and did a few other projects also towards lunar exploration rovers. This is a NASA competition that we joined, which was all in simulation using Gazebo and the ROS ecosystem for looking for resources on the south pole of the moon. And so we had to have those 3 rovers there autonomously driving on the south pole of the moon and looking for resources and bringing those regoliths with water ice back to the lander for processing. So that was a lot of fun. And in this video, I just quickly show, just to give you a sense of those rovers autonomously driving. You can see the simulation environment. And kind of what you see on the bottom is the behavior tree, the internal thinking of the rover. What is the next task I have to do? What is my collaboration with the other rover? So we can talk about this as well more if there's interest. But one point I want to make also, another project was I had the privilege of working with Artifacts, and they're making an amazing platform for CI and simulation, specifically for robotic application, both on Earth and in space. And it allows you to run your tests in a simulation environment, taking all the best practices of software development, but for robotics. So you have a dashboard to keep track of all your results. And an example of a demo we did was tuning a Kalman filter for the localization algorithm of a lunar exploration rover. And it's as simple as defining a YAML file. You put all your parameters here that you want to test. So maybe there's 81 different combinations. You press one button and the whole platform orchestrates that for you. And then you get the results of which combination of parameters gives you good results. You pick the best one, and then you can move on to the next steps of your development. So Fabien is here in the audience. He's working on that, and I encourage you to talk with him. It's like exciting work that they're doing. Last year, I moved to Dubai for a while and joined their team for several months to prepare their mission operations. So you see their flight model over here in their thermal vacuum chamber, in their sandbox. And the main thing we did together was prepare the mission control center in terms of the roles of each operator, their responsibilities, and the procedures to follow, and how to understand the telemetry that's coming from the rover and send the proper telecommands during the 10 days mission on the moon. So we had 24/7 shifts that we practiced with the twin of the rover that was in the gymnasium or in the Dubai desert here. And that was a lot of fun. And unfortunately, in April last year, during the last moments before landing, the iSpace lander that was carrying this rover crashed on the moon. So we didn't have a chance to do the actual mission operations. But we learned a lot, and the team is now working on the second version of the rover going to the South Pole. So that's it for the small rovers. And now just if I still have a few minutes, I can talk about JAOPS, or we can keep it for...
Go for it. If you want to take 2 or 3 minutes for that, and then I have a question for you, if that's okay.
That's good. So now I work at JAOPS. We do mission control software. We have our founding team here. Our CEO is sitting in the front row, as it should. We have plenty of experience, but we can talk about it later. Most point I want to make is we've been building mission control center. The architecture of the one of iSpace is the one Alex has done. But the experience goes back more than 10 years, both in terms of tools, in terms of people. We're basing everything on an open source software. called the JAOPS, which is already used by many companies worldwide. And we make those kind of graphs to set up everything. If you have a mission control center and if you have a mission that's going to the moon, for example, then we can help you set up and train your operators. And another thing we do on top of that is simulation. So we want to provide virtual environments for development, training, and the mission operation itself, which is a good way to simulation provides good videos. So I'm showing that to you. This is an example from we got inspired by Astroscale and their upcoming cosmic mission. So that will be a good segue for the next thing. So you see in here in the simulator, everything is physically simulated. There's no animation. It's not CGI. You have all the forces, the torques, the dynamics, the collisions. So one servicer has this robotic arm that extends and tries to capture this piece of debris, for example. So we provide this so that you can test your algorithms, your navigation algorithms, develop iteratively, maybe connect with the artifacts platform to do CI/CD. And so happy to talk more about this and show you more. And using the same underlying technologies for a lunar surface simulator. And I have a video for that also. I just prepared it 2 days ago specifically for this. So you have just, this is the example of the rover from the Indian Space Agency who did a successful 10-day mission on the moon late last year. And so we recreated that with a bit of artistic liberty. There's also the astrobotic lander on the left side, which unfortunately had an anomaly and didn't make it to the moon. And on the right side, as the rover does a spot turn, you can see appear the Apollo lunar exploration module and the Apollo lunar rover. And there's a guy that's stretching his arms for just giving a sense of scale, how big those landers were in the Apollo times and how small the rovers are now that we're thinking to send. And as we zoom out here, you can see the scale of this environment. There are several kilometers squares of the lunar surface that are simulated, all with craters and slopes and everything. So my last slide is just to recap kind of a JAOPS business model. Now we're doing phase 1 and phase 2 of providing this mission control center services and software training for operators. And in the future, what we plan to do is have our own mission control center with a different lunar exploration missions going there, and all being operated from our mission control center. So with that, I'm happy to get all your questions and open it up for the discussion Q&A whenever it's good time.
Yeah, sure. So I'm going to ask just one question, then we're going to open it up to you guys. And then we'll take Q&A at the end. So originally I was going to ask you basically what is the state of like international collaboration in terms of space exploration with robotics and operations, but based on your presentation, it sounds like it's really robust. To kind of bring it back to Japan, I know, especially big Japanese companies are kind of cagey about releasing what they're working on. So if you had thoughts on that, that would be great, but seems like the answer is yes, things are pretty good. Yeah, unless you have thoughts.
Yeah, there's plenty of collaboration. My personal opinion is there's never enough collaboration. And that's part of the reason also of coming here is trying to find avenues for more collaboration. Definitely in Japan itself, it's still very much growing, very much new for lunar exploration specifically, but already some huge success. For example, the SLIM mission, that was a first in many ways. There is iSpace that's integrating their rover and lander as we speak in Tsukuba now, and they're supposed to launch later on this year. Plenty of rocket companies who are coming there, and then of course in Earth orbit, Astroscale, Access Space, all of these ones. So yeah, plenty of avenues for collaboration, and not only between space companies, but between space companies and Earth companies. Just before I was talking to other people who do operations on Earth. There's a lot to learn from remote extreme environments and regular environments, industrial environments where you need so much reliability. There's a lot of parallels you can draw for space exploration and Earth applications.
Nice. Thank you. And we'll move over to you guys. But I just want you to think about a question for all three of you is think about this for when they get asked at the end. What would be the biggest challenge about doing operations in a space environment? And I know that probably differs whether you're orbiting or whether you're actually on a planet's surface, but think about that and then they'll answer that. But feel free to take it away, guys, Gonzalo and Nico.
Hello. Hi. I will try to make a quick introduction. So my name is Gonzalo Aguirre. I am the Director of Machine Learning and Robotics in Astroscale. And just to do a quick recap of my career. So I studied in Mexico, then worked for a while in Germany, then to do my master's. And through connections, I was able to, in the industry, I was able to come to Japan to do my PhD. I work for Astroscale in robotics and autonomous driving. And finally, now I landed in Astroscale. But one thing that I want to highlight in this is that we're going to talk a little bit about diversity later, but as you can see from my picture 20 years ago when I graduated from Mexico, there are not that many female students of mechatronics at that time. And I think, unfortunately, it hasn't changed enough until now. I can see a trend going up, but I would like to see more. So I am happy to see some female faces here, and I hope that we continue to encourage that. So now is Nico.
Yeah, so yeah, just a little short intro. So I'm from Canada, moved to Japan in 2018. Before that, I studied mechanical mechatronics engineering and worked at the company that made this software called Robot Master. We were doing a lot of offline programming for manufacturing and QA processes. So a lot of inspection, secondary processes in materials for aerospace or automotive. And then I started my MBA, which allowed me to also come to Japan. And I've been working since in logistics and material handling. First at Kyoto Robotics, then Innovtech Studio, more in the warehousing side. And then I joined Telexistence and became the head of engineering there, where we built this robot all the way on the right. The first one was a humanoid, which got a lot of hype, really, really cool kind of construction, which really moved the way that the person would move inside. So it really looked like someone was controlling it when someone was, and it didn't when the robot was just moving on its own. And nowadays, actually, you can see this robot on the right that looks like on a rail with the one arm. Those are deployed in some family marts around Tokyo and a couple across Japan as well. So at that time, around this time last year, I joined ROMS. They're doing kind of nano warehouse, like 100 square meter footprint, kind of what fits in this room. And since November, I joined Astroscale. So kind of making the leap from logistics, material handling, manufacturing, QA into more space and what we're calling on-orbit services, right? So I just want to lead into the rest of our presentation here. So one of the big discussions about space right now is space debris. So why should we care about space debris? And what is space debris? So anything floating around orbit that is uncontrolled or kind of not maneuverable is what we consider space debris. So there are a lot of things up there, some natural ones that become satellites or meteors. And then there's also all the discarded upper stage bodies, rocket bodies that are left floating in orbit. And these aren't small, these are big pieces of junk. They're like the size of a bus. And of course, what happens is those hit other debris and start making smaller debris. And then we also have defunct satellites. So these satellites run out of fuel and haven't made a plan or didn't reach their deorbiting phase. So they're left in semi-stable orbit, something like over 100 years to decay and fall back to Earth. So that's kind of what space debris is. And why it matters is because nowadays, all of our communication infrastructure depends on passing through space. Not all of it, but with the growth of stuff like Starlink, OneWeb, getting satellite internet and connection. We want data faster. Well, we can send it up through space. And one of the big challenges now is setting up these big constellations in space without dealing with debris. So debris is one of the things that's going to be growing, especially in the orbits that matter for us to use for fast, low latency communication. So there are a couple incidents in the past 20 years or so that really started to increase that back in, what was it, 2007? There was a Chinese ASAT. So they deliberately blew up a piece of debris, and it created 3,000 plus more pieces of smaller debris. So these basically turn into small space bullets. They're traveling really, really fast, like kilometers per second. Yeah, kilometers per second, like 8, 12 kilometers per second, more even.
Yeah, like 20 kilometers per second or so.
Yeah, so those ones are really dangerous. So the way we focus on creating on-orbit services, especially for considering space debris right now, we're looking at the bigger pieces, because the bigger pieces become smaller pieces. And these smaller pieces can eventually cause what's been coined as Kessler syndrome. So it's when the density and volume of debris in a certain orbit gets so big, you actually can't use that orbit anymore. There's too much risk of collision. And I think this is one of the things that comes up in operations too for satellites, often changing orbits because you want to avoid near misses with, or collisions with other maneuverable satellites, but also other debris that can be traced. I think one thing I didn't mention is the size of debris that is traceable right now is from ground station or from observation is about 10 centimeters in diameter. Anything smaller than that, we can't see. So I think right now there's about 200,000-ish pieces of debris that can be traced, and the rest are not traceable, but in total, maybe there's another million more, who knows? Yeah, so that's kind of the situation with space debris.
So and now when we lead, so what do we do about the space debris that we have? And well, as Nico was saying, all that dangerous things. So well, we in Astroscale, we are trying to take care of that. And to do that, so I will make a quick introduction of our company. So basically, we are a global company with 7 offices around the globe. We have more than 500 engineers working in each one of in throughout the offices. And so what is it that we are doing is we have a mission. So as Nico was saying, we want to ensure safe and sustainable development of space for the future of for the benefit of future generations. Given the current situation that we have is caused mostly because there is use once and throw away culture in space. So we send a satellite up there and we use it until the end of its life, but then it's very difficult to take it down and people don't care. Also the same for the upper stages. Until very recently, it was not a very sustainable model of development. And there were very few satellites, as Nico was mentioning, or very few launches until recently. But in the past 4 years, we have significantly increased the amount of launches, and this trend will not go down. If anything, it will be the opposite. So how to achieve the vision of a safe and sustainable space? We, in Astroscale, we will focus in the development of the technology, but not only it's important to develop the technology, but also a policy and the business case for this scenario. Why is that? I think that until now, as I mentioned, space debris was not a very big topic. And it has been very critical that our startup also focuses on developing the policy and the markets that make a business case, a useful business case for doing this work. And how do we approach this? So basically, we try to provide all the necessary services for establishing a circular economy in space. Very similar to the kind of economy that we are trying to achieve here on land, we want to achieve the same for space. So we offer services such as removal of existing debris, extending the life of already ongoing satellites to reduce the creation of debris. Also, in the future, we would like to help repair by refueling satellites or swapping out components. And if we look far into the future, we think that we can even establish manufacturing in space through this on-orbit servicing economy. So trying to establish the whole cycle of circular economy in space. And as I mentioned, to achieve this, it is not possible to do it as a single company. And that's why we collaborate with international organizations, space agencies, many governments, and other international organizations in academia and industry.
So some of the technologies that we've already started developing in collaboration with some government organizations, which goes again with the growth and start of injecting policy into space development. A lot of it is driven by government, but then shifts towards commercial space as well as the policy starts to take action. So we have life extension in GEO for fleet management, like changing orbits, looking at refueling as well. We have life extension and in inspection. Sorry, I was looking at the names there, but sorry. In situ space awareness and inspection. So actually right now there's address J satellite in orbit doing inspection for a project with JAXA. I'll show a little clip of that later on. Orbital transfer, like I already mentioned. Debris removal, that's the big one that's growing right now. Cosmic is the project we're doing with UK. You already mentioned Cosmic. And refueling maintenance, we have some project that's starting up with the US government there with NASA. So some of the big technology that we're currently developing, some of it's proven already with RPO and GNC. So RPO is the technology that's driving the other capabilities. It allows us to actually rendezvous with other satellites. These are things that haven't been done autonomously before, where the satellite drives itself, catches up to the other satellite and approaches it. So right now the technology is looking to drive towards this docking stage to be able to capture, right? So we're also developing robot interfaces, docking plates we have already that are being used, actually being distributed as well into other commercial use satellites for future planning of end of life services, so decommissioning or possibly refueling. And yeah, like I mentioned, autonomy, looking at how to build this autonomous operation as well. One of the challenge in operation as well, you don't have 24-hour communication with your satellites due to the nature of the orbits and the position of your antennas. And of course, ground segments. So this operation stations, control stations, and the process that goes behind it. So just to look at some of the ones that we're currently working on, we see this approach, capture, and interface are kind of the big ones that are coming up right now that go for all of the first, not easy, but the first proofs that it can be done, that we can go and meet up, capture, interface, dock with something floating in space, prepared or unprepared. So a prepared piece of equipment might have a docking plate or an interface, whereas an unprepared one, there's no way to know. And that's why we also have ISSA, which is more of an inspection type of service. And that's the mission that we have now with Address J. And ground segment, control center and ground stations. So ELSA-D was our first satellite mission. It was self-funded. Currently, it's in the deorbiting phase, and it's already completed its mission. It demonstrated the docking plate. It demonstrated this autonomous recapture of this device. So it actually went up there with its own piece of debris with a docking plate, released it, recaptured it, released it, lost it, found it again, and then went to capture it again. So that's kind of the whole kind of technology proof of concept. Address J, who is up there right now, is currently chasing down our target, and its mission is to take images for JAXA. ELSA M, currently working with UK to do end-of-life services for various communication satellites in orbit. LEX, refueling in GEO, commercial again, in the US, and Cosmic, which we talked about, is the first big government-funded ADR, active debris removal service to go actually remove defunct satellites from orbit. I just wanted to, at this point, just show something really interesting that that was posted on LinkedIn. So this was actually posted by an amateur astronomer. And so he was able to capture in his telescope our target, Address J, in orbit. So this is actually visible on a really, really clear and really, really dark night. You can see this with your naked eye if you squint. But if you got a telescope and a camera, you can set that up too. Pretty cool. We're chasing, yeah. The chase is on.
How long before you would catch up to your target in that case?
In the coming weeks.
Okay.
Yeah. Very soon we have started now the RPO, so it's the final approach.
Yeah, so they've already started rendezvous. So we've already done rendezvous. Now we're doing RPO. So now it's doing this approach to basically come really close to it, prove that technology again. But with this piece of junk is unprepared. So it's a H2A upper stage from JAXA that was launched, and it's been floating around in space for like, I don't know, 15 years or something like that.
Yeah, it's an 11 meters long, 4 meters wide, 3-ton piece of junk.
Is every mission that gradual? Because in my mind, hearing about what you do, I figured something goes up there, it zooms up, it catches it, maybe it takes a few hours. But it sounds like this is extremely gradual over time. You're basically doing, it sounds like what would be the equivalent of a multi-stage liftoff, but in orbit where you're successively activating different rockets to catch up to something. Do you also have ways to slow that piece of debris down, or are you always playing catch up to its speed?
No, you actually do have to catch up to it. And what you mentioned in this chasing is basically the what is will be called like the run matching. So like we are approaching the debris and trying to catch it, but we have to do it in such a way that is safe because there is a lot of uncertainty about what you can see from the ground and what the GPS is telling you, and there is a lot of uncertainty basically there. So for example, one of the things that we do is that we create a safety ellipse. So the target is here, but basically we oscillate around it while we are trying to catch it, so that if we mistake it, we will just basically fly by without a problem.
Related, sort of, but more sort of just exploratory. Have you ever had an issue where unexpected space debris has interfered with a mission to capture like expected space debris? Like maybe one of those, sub 10 centimeter objects comes out of nowhere and messes you up?
So I would say that it's highly likely that that may occur. There's a lot that we can't know about what's floating up in orbit because it's too small to detect. And that's one of the things about ISSA or SSA, it's in situ awareness, is also looking at what's up there from the point of view of someone up there. Because right now, most of all the observations done from ground. Yeah. So
Awesome.
even many companies who are providing this like satellite tracking from ground, they're only mainly doing it from ground stations, telescopes, and maybe other companies are sharing their GPS data. So yeah, what we're able to collect as data to determine if we may collide with another satellite is coming from this data.
Yeah, we get regular updates on what is called conjunction data, and it's like the probability as you are coming closer and closer that there will be a collision, and then you have to make a decision whether you do a maneuver or just let it go. And regarding to that topic, so there has been maneuvers with ELSA-D definitely, and also like we see that because of the amount of this, debris that it is out there, the windows of launching rockets are getting shorter and shorter and shorter. So like sometimes you only have a 15-minute window where you can launch the rocket, or wait until the next month or the next days or the coming days where it will be possible to launch the rocket. And that causes delays on missions of not only us, but many other people as well.
Fascinating. I have a bunch more questions. I'd like to also open it to audience Q&A. Would that be okay with you guys?
We had a couple more slides.
Yeah, if you want to go through in maybe like 2 minutes, and then we'll
sure
take some audience questions.
So this is kind of recent news. There was a bunch of funding that was going towards this OSAM ADR development, and they just cut it. So a bunch of startups are now looking at how do we capitalize on claiming some of this reissued funding for space program. And one of the reasons is that NASA decided that it was too costly for them to do it themselves or outsource it from within their organization. And many other companies have already started doing this type of development as well. And this kind of maybe goes into some of your Q&A. What are some of the challenges in robotics in space? So did you want to take any of the other slides, or? Yeah, I think we'd come back to this one.
That was basically my question. It's going to
Yeah.
be challenges.
Yeah, so there is a bunch of challenges from the doing robotics in space, and to help mitigate those challenges, we think that machine learning offers a lot of like new opportunities on advancing autonomy and every one of the key technologies that Nico mentioned earlier. So, but there is a very difficult challenge to using machine learning in space, and that's it, the scarcity of data. So machine learning has the possibility of contributing to all the mission life cycle from the development phase all the way to the end of life. However, due to, let's say, for example, there is very few cooperation between agencies and companies at this point. So it's difficult to share that data. On top of that, there is very few people that has actually taken data like the one that ADRAS-J is going to take now. So this is one of the first on its type missions where we are going to go and look at an actual piece of trash on the space. And nobody has done before from the distance that we're going to do it. And that kind of data is super valuable for machine learning, but the data is still not available. So we are relying a lot on simulation and generative tools for creating data for feeding machine learning systems. But in the future, it will be very critical that we all work together and create that kind of databases that are fueling machine learning systems in ground. So that's kind of important. And we hope that right now we are just doing simple demonstration missions and proving the technology. But if we look 10 years or 5 years, more in the future years, we think that we are going to be able to do incredible things such as manufacturing in space, building bigger telescopes than the James Webb, for example, that was built still on the ground. And it's very difficult to launch this kind of super big structures into space. So as we look into developing different kinds of technology, the only answer is to do manufacturing on space and have this circular economy will really help to drive that. Well, thank you.
Elliptical economy, if it's
elliptical.
Thank you very much. That actually does answer two of my big questions. I have more, but I'd like to open it to audience Q&A for now, and then we can come back to it if.
Yeah. And I just wanted to keep this
Yes,
slide
please.
up because I think this kind of sums up some of the interesting challenges of space. And
Perfect.
yeah, please bring up your questions and we're happy to
Thanks.
take them on.
Does anybody have any questions? You could just shout it out in the room and then I'll repeat it for the viewers online. Yes. So the question was the cycle of what you're doing. You can catch up to and catch the debris, but how do you actually remove it from space?
Yeah, so actually this is part of the active debris removal projects. And what we do is called deorbiting. So we carry it into a safe degrading orbit. And so right now, most of this is done in low Earth orbit, which is basically 200 to 600 kilometers from sea level. And there's still thin atmosphere there. So when you bring it low enough and slow it down enough, the atmosphere starts creating drag and slowly it falls, gets pulled back to Earth.
So as just to build a little bit quickly on that. So as we mentioned, right now we are still on demonstration mission. So the approach right now is that we take it down with us. So our missions will basically take the debris and burn down in the atmosphere together. But in the future, this is not a very sustainable way of dealing with debris. So in the future, there should be like a more distributed architecture where we use like a smaller sort of spacecrafts to lower and keep the servicing spacecraft doing more missions.
Thanks. Yes. So the question was, on average, over the lifetime of one of your devices, how many pieces of debris can it capture? And what happens when that lifetime is over? Is there refueling plans, or how do you, I guess, avoid becoming debris?
So yeah, at the moment it's only one, as I mentioned. So for our demonstration and early missions, we will be only doing one single removal. But in the future, the plan is to have a fleet, let's call it, of satellites performing multiple maneuvers, being refueled, and eventually they will also deorbit themselves. So right now there are guidelines for the orbiting time, and we try to fully comply with those. So the satellites automatically will also enter into the orbiting phase within a period determined period of time.
For example, ELSA D, I think deorbiting time now is 5 years is the limit. Likely it'll fall faster than that, but it pushed itself into stable deorbit. So yeah, and the mission continues until its end of life. So it's still being monitored, and we're following where that's going. Yeah, there's also simulations for where it falls. So that's maybe that the follow-up question on how do you bring it down, and then where do you put it, right? So most times we aim for somewhere in the ocean.
Most times. Before we move on to another audience question, I want to bring it back to Luis for a second. So we see here challenges of robotics in space in an orbital situation. When you're designing for land-based, so say you're on the surface of the moon, what are the most unique challenges as opposed to designing, say, a rover or an arm or something like that on Earth?
So challenges are challenging. So there's a lot of them. All of the challenges that were on the slide here from the Astroscale guys, perfect. They're all there also for Lunar Rover. The environment is different, so the intensity of the challenges is maybe different. The temperatures are different, or the cycles variations are different. But there's all the same challenges, and on top of that, you get new ones. For example, the lunar dust, something they don't have. There's many different aspects. Yeah.
Can you say something about the dust in terms of how fine it is and what it'll do to your motors if it gets into the joints?
Yeah, that's something we spend a lot of time. There's a iSpace patent about how to avoid getting the dust inside the motors, because it's such a fine abrasive dust particles that if it gets inside, it will wear out your bearings. It will cut down your electric connections. So it's basically game over. So there's several seals, several layers of seals that make sure no dust goes inside. The dust itself is basically the same sand you have on the beach, but instead of being nice and round, because there's erosion processes on Earth with water, with wind, but there's none of that on the moon. So instead of having round particles, you have shards of glass, basically. The only way they break them down is the same way you break down a piece of glass. Mm-hmm. So micrometeorites or solar wind or things like this. So it's all small needles that try to get into you. And the Apollo astronauts, for example, when they went and did their spacewalks, several hours, they came back in the lunar exploration module, the lander. They were covered by dust because it sticks. It's electrostatically charged, so it sticks to your spacesuit. And then it floats around in the. It smells like gunpowder, and they all had some kind of coughing and respiratory problems. It makes holes in your lungs, so you don't want to breathe it. You want to remove as much as you can. It's terrible stuff for electronics, for humans, for everything.
So you heard it here first. The moon is covered in shards of glass and needles.
Yeah. Let's go.
Yeah. We only have about 1 minute left. You can jump in.
I have a question for Louis, like something that he was mentioning about the compression of video to be able to monitor the progress of the operations. So the problem a lot with the space robotics, besides the ones that are listed here, is also that we don't have the capacity to iterate quickly, like by sending many robots and everything. And also this plays to the telerobotics that it's being pitched here as an intermediate solution in companies in the ground. So what do you see? Do you think that there will be the same kind of development between using telerobotics as an intermediate step in this development until we reach full autonomy? I am assuming that full autonomy is the goal, but what do you think about these transitions?
I see it as a collaboration between robots are good at doing robotic jobs and humans are good at doing human jobs. So and then on top of that, there's a latency, as you said, we're 380,000 kilometers away. So it's best case 3 seconds round trip. So sometimes 3 seconds latency is the difference between you crash or you don't crash in the rock that's in front of you. So definitely you have to have some kind of autonomy on board, this kind of emergency stop to at least detect a dangerous situation and stop and wait for human feedback. So this middle ground between collaboration between fully autonomous and fully teleoperational, there's like, for example, supervised autonomy. So low-level functions are made on board by the rover, but we have operators in the mission control room who monitor the rover, explains its plan, where it's going to go, what kind of obstacles it sees, and the humans use their human ability to make sense of that data and to give more high-level goals, like go and explore this interesting rock that the scientists discovered, and go and use this payload science instrument, this drill over there. So I really see it as not a 100% black or white, robotic or autonomous, but collaboration and using the skills and the advantages of both.
Fascinating. So hope for humans still that we have a place in operations and other things. We can leave it there. Thank you, everyone. I'm sorry we didn't get to all the audience questions, but this was fascinating. I learned a lot. Please talk to us after the panel, and then please also search for Robotics X Tokyo on both LinkedIn and Meetup, and you can find all our events listed there. But I'd like to get a round of applause for all these guys, please, if that's okay. Thank you. And that's it. Please enjoy the rest of your night. Thanks.